I'm sorry, the title of my talk has been changed a little bit. As in the previous talk of Istvan Kovac, my talk is concerned with Cayley isomorphism property, but for central Cayley graphs over finite simple groups, and with Cayley representations of these graphs. The talk is based on joint work with Andrei Vasilyev. And first of all, I would like to mention that in some sense, the results from the talk are corollaries of the results obtained by Ilya Ponomarenko and Andrei Vasilyev 3 years ago, when they started to study the isomorphism problem for central Cayley graphs over simple groups. Let's start with some definitions and notations. I'm sure that everyone here knows them, but to make the talk self-contained, I will recall them quickly. Let G be a finite group and S an identity-free subset of G. By the Cayley graph over G with connection set S, we mean the digraph with vertex set G and arc set consisting of all pairs of the form G S multiple G, where G runs over all group G and S runs over the set S. By G-right, we denote the subgroup of the symmetric group of the set G, consisting of all right translations of G. And first, easy observation: if gamma is a Cayley graph over G, then its automorphism group contains the group G-right. A permutation group is said to be G regular if it is regular and isomorphic to G. And further throughout the talk, for a given permutation group K, we will denote by reg of K and G the set of all G-regular subgroups of a permutation group K. The classical Sabidusis theorem can be formulated in these terms as follows. A digraph gamma is isomorphic to a Cayley digraph over a group G if and only if the set reg of the automorphism group of gamma and G is non-empty. So let's move to Cayley representations. A Cayley representation of a digraph gamma over a group G is an isomorphism from gamma to a Cayley digraph over G. And two Cayley representations, say F1 and F2, of gamma over G are equivalent if the images of gamma under F1 and F2 are Cayley isomorphic. This means that there exists an automorphism of G, which is at the same time an isomorphism between the images of gamma under F1 and F2. Note that if two Cayley digraphs are Cayley isomorphic, of course they are isomorphic. However, the converse statement is not true in general. And the first K-knot theorem on Cayley representations was proved by Laszlo Babay in 1977. The first item of this theorem: Cayley representations of a digraph gamma over a group G are in one-to-one correspondence with G-regular subgroups of the automorphism group of gamma. And the second item: two Cayley representations of gamma over G are equivalent if and only if the corresponding G-regular subgroups are conjugate in the automorphism group of gamma. So this theorem reduces studying of Cayley representations to studying of regular permutation groups. And to check whether two Cayley representations are equivalent, we need to check whether two regular permutation groups are conjugate. So The problem of finding Cayley representations can be formulated as follows. Given a group G and a digraph gamma, find a full set of non-equivalent Cayley representations of gamma over G. This problem we denote by CRG. It seems that in general this problem is very hard and not so much is known on efficient solution of this problem. Note that recognition problem for Cayley digraphs is a special case of the problem CRG. From Sabidusi's theorem, it follows that a digraph is isomorphic to a Cayley digraph over G if and only if this Cayley digraph has at least one Cayley representation over G. The problem of determining whether a Cayley digraph gamma over G and an arbitrary digraph, say gamma prime, are isomorphic is reduced to the problem CRG in time polynomial in the order of the automorphism group of G. In particular, if G is generated by a set of at most constant size, then this reduction can be done in time polynomial in the order of G. So we can see that the problem CRG is harder than the recognition and the isomorphism problem for Cayley digraphs. Nevertheless, this problem was solved efficiently in some special cases. I think the first result on this problem was obtained by Sergei Evdokimov and Ilya Ponomarenko 17 years ago. They constructed a polynomial time algorithm for solving CRG when the group G is cyclic. Also, this problem was solved for the direct product of the elementary abelian group of order 4 and cyclic group of prime order. This was done by Roman Nedela and Ilya Ponomarenko. And for the direct product of cyclic P group and cyclic group of order P, where P is equal to 2 or P is equal to 3. In all these cases, the constructed algorithm deal with permutation groups. In fact, these algorithms find the full set of pairwise non-conjugated regular subgroups for a given permutation group. I think now it's time to say some words about Cayley isomorphism property. A subset S of a group G is called a CI subset if for each subset T of G, the Cayley digraphs over G with connection sets S and T are isomorphic if and only if they are Cayley isomorphic. So let S be a subset of G and gamma the Cayley digraph over G with connection set S. Some easy corollaries from the definitions. S is a CI subset if and only if gamma has a unique Cayley representation over G up to equivalence. And in terms of permutation groups, S is a CI subset if and only if all G-regular subgroups of the automorphism group of gamma are pairwise conjugate in the automorphism group of gamma. Why CI property is important? If gamma prime is another Cayley digraph over G, then one can test whether gamma and gamma prime are isomorphic in time the order of the automorphism group of G multiple to the polynomial depending on the order of G. And again, if G is generated by a set of at most constant size, then this isomorphism can be checked in time polynomial in the order of group. To verify the isomorphism between a K-Led graph with CI connection set and any other K-Led graph of the same group, we only need to check all group isomorphisms. Usually, the order of the automorphism group of G is much less than the number of all permutations. So, the CI property was studied almost 50 years in many papers by many authors, and Istvan made a very nice survey on this problem. What is the central K-Led graph? Let G be a finite group. A subset S of G is called normal if S to the power G is equal to S for every G from G, like normal subgroup. And a K-Led graph is said to be central if its connection set is normal. Why set is normal but the graph is central? On the one hand, the term normal graph is used in case when the group G right is normal in the automorphism group of the graph. On the other hand, if we consider the Schur ring corresponding to the central K-Led graph, this Schur ring lies inside the center of the group ring. So this explains the choice of the term central. By G left, we denote the subgroup of the symmetric group of the set G, consisting of all left translations of G. And by sigma, the permutation on G which inverse every element. Clearly, the order of G is equal to 2. It is easy to check that G right and G left are conjugate by sigma. By G star, we denote the product of G left and G right. This product is defined correctly. And if gamma is a central K-Led graph over G, then its automorphism group contains G left and G right, and hence it contains G star. And if S is a normal subset of G and S is close inversed, then permutation sigma belongs to the automorphism group of the corresponding K-Led graph. And hence G right and G left are conjugate in this automorphism group. So I think this is all necessary information on central K-Led graphs. I will recall what is a simple group. A group G is called simple if G has no proper non-trivial normal subgroups. The circle of G is a subgroup generated by the minimal normal subgroups of G. And a group G is called almost simple if its circle is a non-abelian simple group. And the first result on the isomorphism problem for central K-Led graphs, not only over simple groups, but over almost simple groups, was obtained by Ilya Ponomarenko and Andrei Vasilyev 3 years ago. They proved that for any two central K-Led graphs, gamma and gamma prime, over explicitly given almost simple groups G and G prime of order n, the set of all isomorphisms from gamma to gamma prime can be found in time polynomial in the order of groups. So, and as a corollary, they obtain the following statement. The automorphism group of a central K-Led graph of an explicitly given almost simple group of order n can be found in polynomial time again. In some sense, we refine this result for simple groups. So let's move to main results. The main theorem. if G is a simple group and gamma is a central K-Led graph over G, then its automorphism group coincides with the all-symmetric group of the set G, or every G-regular subgroup of the automorphism group of gamma is equal to G left or G right. So in non-trivial cases, we have at most two distinct G-regular subgroups in the automorphism group of a central K-Led graph. Of course, if G is abelian, then G left is equal to G right. The first corollary states that every central K-Led graph of a simple group has at most two pairwise non-equivalent K-Led representations over G. I think this statement is clear. So in view of Babay's theorem, so every K-Led representation is associated with G left or G right. In the latter case, sorry, but in the former case, clearly all G-regular subgroups are conjugate in the symmetric group. So, and up to equivalence, we have only one K-Led representation. And the second corollary, if G is a simple group and S is a normal inverse closed subset of G, then S is a CI subset. Since S is normal and inverse closed, it contains the automorphism group of the K-Led graph with connection set S contains permutation sigma, which inverse every element from G. This means that G left and G right are conjugate in this automorphism group. So we have exactly one G-regular subgroup in the automorphism group of the graph up to conjugation. This exactly means that S is a CI subset. So, and in the remaining time, I will provide the sketch of the proof of the main theorem. The proof is based on three K-knot lemmas, but before I provide one more notation. By D of 2 and G, we denote the subgroup of the symmetric group of the set G generated by the holomorph of G and permutation sigma, which inverse every element from G. The first K-knot lemma was proved by Ilya Ponomarenko and Andrei Vasilyev in the same paper. They proved if G is a non-abelian simple group and gamma is a central K-Led graph over G, then the automorphism group of gamma is equal to the symmetric group of the set G, or it is a subgroup of D of 2 and G. So this means that in non-trivial cases, the automorphism group is quite small. The second K-knot lemma can be formulated as follows. If G is a simple group of order n, then the order of D of 2 and G is at most 2 multiple n square multiple logarithm n. This lemma follows from the description of automorphism groups of finite simple groups, and here we use the classification of finite simple groups to check this property. And the third K-knot lemma, which was proved by Fried, Guralnik, and Saksel 27 years ago. Let G be a non-abelian simple group. There exists an involution T from G such that the automorphism group of G can be presented as the product of the group of inner automorphisms of G and the centralizer of T in the automorphism group of G. And using these three lemmas, we proved the main theorem. Firstly, if G is abelian, then clearly it is isomorphic to a cyclic group of prime order, and in this case, every subset of G is Ci. This was proved by Elshpash and Turner. And this fact implies almost directly the required statement. By K here, we denote the automorphism group of a central K-linear graphs of a simple group G. If K is not equal to the symmetric group of the set G, then lemma 1 implies that K is a subgroup of the group D of 2 and G. We show that G star is normal in D of 2 and G, and G star is the direct product of G left and G right. I think this is clear because G is a simple group and G left and G right intersect trivially. Let H be a G-regular subgroup of K, of the automorphism group of our D graph. Clearly, the intersection of H and G star is normal in H, because G star is normal in all group. Since H is simple, H is a subgroup of G star, or the intersection of H and G star is trivial. In the latter case, the order of the product of H and G star is equal to n cube, which is greater than 2 multiple n square multiple logarithm of n, and we obtain a contradiction with lemma 2. Thus, we have that H is a subgroup of G star now. And the last step. Suppose that H is not equal to G left or G right. Then, in fact, H is a subdirect product of G left and G right. This means that there exists an automorphism tau of G, such that H consists of all elements of the form GL, G tau R, where G runs over G. GL is the left translations by the element G, and G tau R is the right translation by the element G tau. So let us choose an involution T from G as in lemma 3. Lemma 3 is presented on the top of the slide. The automorphism group of G can be presented as the product of the group of inner automorphisms of G and the centralizer of T in the automorphism group of G. In particular, the automorphism tau can be presented as the product psi and phi, where psi is the inner automorphism of G and phi belongs to the centralizer of T in the automorphism group of G. Let X be the element of G corresponding to psi. This means that psi acts by conjugation of X. And let H be the product of TL and T tau R. Again, TL means the left translations by the element T, and T tau means the right translation by the element T tau. And we show that if T is not equal to X, then H fixes the product Tx. And if T is equal to X, then H fixes T. And we obtain a contradiction with the fact that H is regular. So I think it's a good idea to stop here. Thank you for your attention.